Dear students, we have discussed gradient, divergence and curve concepts already in previous videos. All this operator will use del operator. So in this video, I would like to discuss about Laplacian operator and how it will apply on scalar field function. Let me know about what is a scalar field. In mathematics and physics, a scalar field associates a scalar value to every point in a space. Scalar fields are required to be coordinate independent. Example, temperature. Temperature field is a scalar field. As you are observing, every location has an associated value. Colors in the globe map shows different surface temperatures. Density of a body, pressure field, these are all scalar fields only. As you are observing, scalar fields are represented by contours. The colors represent the surface temperatures and the color lines show the constant temperature. As you know, Earth is surrounded by magnetic field and gravitational field. And the physics says there are many scalar fields in the universe which we don't know. Mathematically, we represent the scalar field by t equals to t of x comma y comma z, or it may be the t may be equal to n number of variables also. Even we can extend for n number of variables. Example, sine of x y z, x squared plus y squared plus z squared, etc. Let me see how the Laplacian operator will be applied on a scalar field function. As we have a scalar field function phi of x comma y comma z, gradient of phi is a vector field. Gradient of phi will give us dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. Whereas the divergence of gradient of phi, when the divergence operator is applied on a gradient of a function, we will get the Laplacian operator. Laplacian operator is dou squared by dou x squared plus dou squared divided by dou y squared plus dou squared divided by dou z squared, and is called the Laplacian operator, which was first applied to the study of celestial mechanics by Pierre-Simon Laplace, a French mathematician and astronomer of 19th century, and has been named after him. Why is Laplacian important? Laplace operator has since been used to describe many different phenomena like a wave equation which governs things like the music that is made from guitar twisting. It also governs electromagnetic waves and a diffusion equation for heat and fluid flow and quantum mechanics. And the Laplace equation is widely used in celestial mechanics. And the function which satisfies the Laplace equation is called the harmonic function. which people widely used in complex analysis. Let me see few problems on Laplacian operator. Compute Laplace square of a scalar function x square plus y square plus z square. Let me consider a function and the Laplacian operator Laplace square will be applied on a scalar function. So it gives us dou square by dou x square of x square plus y square plus z square plus dou square divided by dou y square of x square plus y square plus z square plus dou square divided by dou z squared of x square plus y square plus z square. In the first term, we would differentiate the function partially with respect to x, keeping other two variables as a constants. So as we differentiate it first time, we get a 2x. Then on second differentiation with respect to x will give us 2. Similarly, here to 1 and then on again second differentiation 2. For the same third term, as we differentiate it with respect to a z twice, we get a 2. So thereby we get 6 as the answer. And in the second problem, you are evaluating the operator about the point 1, 1, 1. Let me go to the third problem. If the function phi of x comma y comma z has been given as 2x cubed y squared z to the power of 4, then find divergence of gradient of phi. So divergence of gradient of phi is nothing but Laplacian operator. So as you differentiate the function phi with respect to x, y and z, thereby you will get a gradient of a phi. So gradient of a phi is a dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. So getting a gradient of a phi, then taking divergence for the gradient of a phi. Taking the divergence, we get a Laplacian operator. So divergence of a gradient of a phi will give us the Laplacian operator itself. Let me see one problem where the operator will be applied on the r to the power of n plus 1. So it will give us n plus 1 into n plus 1 to r to the power of n minus 1. As we know that the position vector of the particle at any point in the space is being defined by the vector r equals to x I cap plus y j cap plus z k cap. So as you take the mod of that, you will get square root of x square plus y square plus z square. So it will give us r square is equal to x square plus y square plus z square, where r is a function of x, y and z. So when you differentiate it to this with respect to x, dou r by dou x, you will get x by r. If you differentiate it with respect to y, dou r by dou y is y by r. And if you differentiate it this with respect to z, you will get a z by r. So first step is when you differentiate it first partially with respect to x, r to the power of n plus 1. So you will get n plus 1 r to the power of n plus 1 minus 1. As a result, you will get r to the power of n. Then we will differentiate it r with respect to x, that is dou r by dou x. So we have an idea by the given in the problem, okay, r equals to mod of r. By that result, we will come to know that dou r by dou x is x by r. So on simplifying, we will get 1 plus n plus 1 of x into r to the power of n minus 1. Similarly, if you differentiate it second time, now keeping out n plus 1 as a constant, okay, outside, and using the product rule, we'll get x to the power r to the power of n minus 1 if you keep a constant, and differentiation of x is 1. And for the second, x if you keep a constant, and when you differentiate r power n minus 1, it is n minus 1 into r to the power of n minus 2 multiplies with x by r. Thereby we get n plus 1 of r to the power of n minus 1 plus x squared into n minus 1 r to the power of n minus 3. Similarly, on differentiating with respect to y, with respect to z, we will get the terms correspondingly. N plus 1 of r to the power of n minus 1 plus y square of n minus 1 into r to the power of n minus 3, and n plus 1 of r to the power of n minus 1 plus z square of n minus 1 into r to the power of n minus 3. So if you add all the three terms, we are going to get n plus 1 into n plus 2 with a r to the power of n minus 1. So by taking n equal to a minus 2, we get nabla square of 1 by r as 0. Similarly, many special cases can be derived with the help of this result. Let me see in this problem how the Laplacian operator will be applied on a function of a function f of r. So you know that where f is a function of r. So first we have to differentiate the function, and then we have to differentiate the function r term with respect to x. So as we know already, r is equal to a mod r. So thereby r square is equal to this x square plus y square plus z square, and 2r into 2r by dou x, whereas dou r by dou x is x by r. When you differentiate the function f of r with respect to x, first we differentiate it with respect to function f dash r, and then with respect to r as a dou r by dou x. So as we have the relation r square equal to x square plus y square plus z square, so thereby dou r by dou x is x by r. Similarly, on differentiating again with respect to x, okay, f dash of r keeping constant and differentiating x by r. So by quotient rule, we will get r minus x into dou r by dou x divided by r square plus x by r if you keep constant, and when you differentiate it f dash of r, so we'll get f double dash of r, and then differentiating r with respect to x, dou r by dou x we will get. So this is a second order partial derivative with respect to f of x for f of r. Similarly, we will get a second order partial derivative on simplification. Similarly, we will get with respect to y, with respect to a z, and on adding all this, we get a equation. Let all of you practice these two problems, and if you have any doubts, we will discuss further.